Welcome everyone to the virtual IoT webinar. Today's webinar is introducing an open platform for your SCADA project. And I'm here with Jürgen Rose. You can ask your questions on Twitter, #virtualIoT, or on the Hangout Q&A, and then we'll answer them at the end or via email afterwards. So Jürgen, go ahead.
Hi, I'm Jürgen from IBH Systems, and I welcome you to our webinar. And I want to talk a bit about what Eclipse SCADA actually is, and then I want to show you how you can actually start with it and go right into it with configuring some devices and how to visualize it. My colleague is at the moment not with me, so I'm doing it alone. He's at the moment preparing our talk for the EclipseCon Europe. So I'm just starting with the slides. So I want to first explain what is actually SCADA. SCADA means supervisory control and data acquisition, and is defined as the monitoring control of technical processes by means of a computer system. This is pretty long, but still a bit shorter than the version in the English Wikipedia. So I just took the translation from the German article. So what does it actually mean? If you talk about SCADA, then this is something like that. So you have a lot of, you have a plant, for instance, a lot of devices, and you have some monitoring, you have control, you want to know what's going on with the devices. So you have a central point where all the data gets aggregated and also visualized to the operator. So the operator has to know what's going on, he has to know the values, he has to know if there are some alarms on the system, if everything works fine, or if there are any problems. And if we have a look at the picture, this is a pretty old picture, how it was done in the past. The modern SCADA system doesn't actually look very much different from that, because there's a lot of experience in it, and the operating principles behind it are still the same. The only difference is that now the SCADA system itself is software for most parts, and is running on a server, and the visualization is now on the client side, and the operator has some piece of software which is installed, or from a web page, for instance, in more modern systems, and he can trigger actions and monitoring what's going on. So, in short, Eclipse SCADA itself is an implementation of a SCADA system based on the Java platform. It's an open source SCADA platform. We use a lot of Eclipse technology. That was the reason we actually moved to the Eclipse Foundation. With it come some protocol implementations, there are server components, there are client libraries, and a lot of stuff more. Then we have some utility projects, and we have the tooling around it. We have the Eclipse SCADA administration client, and we have the configurator, which is there to configure your system, define where your devices live, and how to access them. The goal is to provide a comprehensive, state-of-the-art SCADA system built on modern technologies. And we want to be open to interface with as many systems as possible. The original use case, and this is very much a thing where Java is very good in, is to allow the easy integration to business applications, for instance, ERP systems. And on the other hand, we have the hardware. And so our goal is to put both of these things together, to connect the hardware with business applications. But that's only one part of it. When we have a look at what actually, of which parts Eclipse SCADA consists, we have the data acquisition part, which is responsible for pulling in all the data from all the devices which are accessed via some kind of protocols. Then on top of that, we have alarms and events. So it looks at the data and if there are any violations of levels or constraints or whatever. You have an alarm and then an event, for instance, gets generated. Then we have the historical data interface, which is responsible for recording those data. Then we have the configuration. Sorry about that. Then we have the configuration, and last but not least, we have the UI, or HMI as it's called in SCADA terms normally. So the data acquisition part deals with real-time data and basically handles single scalar values. For instance, you have a sensor value from the thermometer or temperature sensor. You have one value from it, which is the temperature. You have a density meter. You have one value, which is the density. Additionally, you might have some additional attributes, but that's secondary to the primary value. The alarms and events framework handles process alarms. It handles operator actions like acknowledging of those alarms which are generated. It shows responses generated by the system, informational messages, auditing messages. So you can define at what range a value is actually valid, and if it exceeds those ranges, it generates an alarm. The historical data is responsible for recording the values which are acquired by the DA system and archives these for later retrieval, which is also included in that part. For instance, you can then show the change of the values in some chart or whatever, or doing other calculations on it if you like. Then we have the configuration system, which handles the creation of configuration for the server, which is actually of two parts. We have the creation of the configuration and then the configuration on the server itself, which is also which allows us to reconfigure most of the running system during runtime. And again, we have the visualization, which provides ready-to-use UI components based on Raw2D, and you can just pull them together. It's very scriptable. You can use JavaScript to animate all the stuff, and then you can also use this to build a client application, which you can then deliver to your customer or to the operator or however. The central piece to all of it is data access. Essentially, if you go back and look at the features, you can use them on a case-by-case basis, but the underlying thing is still data acquisition. And all the other functionality, generating alarms, whatever, it's based on the values which are provided by it. And just to demonstrate it, we will create a project and see what we can actually do with Eclipse SCADA. So it's demo time. So just have a look at the Eclipse SCADA website, where you can get all the stuff. You have the download area, where you get the links for the update repositories, which you can then use to install all the necessary Eclipse SCADA components in the plain Eclipse IDE. I already did it, because if I show it now, then it would just take too long. So I've prepared IDE, and I'm now creating a SCADA project. The basic idea is now that, let's say, one of the most common protocols in the field out there, even if it's one of the oldest, but it's also one of the simplest, and I guess that's the reason why it's still used today, is Modbus. So what I did was, because I don't have an actual Modbus device here at the moment, I took our Modbus test slave, and I created now a Modbus device which just has two registers. So we have register 0 and register 1, both 16-bit as it is with the Modbus, and we want to connect to it. So we have, let's say, two values on it. You can change it here. Just to show you that it actually works, I start and use a third-party tool to connect to it, and as we can see, the value actually has changed. It's 8 and 9, and if I change the value here to 10, we have 10 here as well. And what you can see here is that Modbus works in a polling mode, so you have to request the values, and then the Modbus device will send you a response. Eclipse SCADA itself is totally event-driven, but of course, when we want to connect to some device which only supports polling, then we can do that as well. But what we do then, we translate it into an event-driven fashion. So I'll show you how we connect to such a Modbus device. What we do first, we create a new SCADA project. So this is the Eclipse SCADA configuration project. Webinar. And what it creates is ready-to-use configuration. There's already some stuff pre-configured. It's not very usable for us, so we are going to delete all the stuff and create our own things. But just to show that it actually does something, I am going to create the configuration, and if you have a look at the output directory, you can see that for each system node we have, they get some configuration artifacts generated. Just to show you the general principle. So the first thing is we delete all the stuff, and scratch. The two basic, all the configuration is based on EMF, and so it's it uses basic EMF tooling, and the basic idea is to have two models which then get merged together to create the actual model, which gets then translated to the configuration artifacts. So we have on one hand the infrastructure model, which defines what kind of devices I have actually in the field, and the other one is the component model, which defines how I want to name my items, my tags, and how they are hooked up together. So what I'm going to do now is to actually hook up my my Modbus device. I configure this as an external node, and I want to put the Modbus device. I just defined that this is my Modbus device. And in the real world, this would be some IP address on your network. In this small example, this is of course localhost. So I put it on the local IP address. Modbus usually uses the 502 port, TCP port, and I give it a name as well. So what I need now is to define how the device actually looks like. We want to have a mapping from the names, from the register numbers to the to some kind of sensible names for us. For that, I have to create a type system, and this is what I'm doing. I create a memory type model. Oops, sorry, wrong button. Types. So this memory type model is actually used for each PLC, which essentially is based on a communication protocol where blobs of memory transfer. So we say we have a blob of memory, and we want to define how the memory itself is essentially structured. So it's basically a thing C structs. So we can define a type definition, and we have some variables. So this is basically the struct. You can give it some name, and the type system also gets a name, so you can find it later a bit more easily. And we name it variable v1 and variable v2. And we say we want to have a 16-bit unsigned integer, which is basically the same mode as Modbus operates. The only thing which we have to consider, because Modbus registers are not 8-bit but 16-bit, is since the memory model operates on bytes, we have to multiply the index by 2 to get to the actual address. So it's not a perfect fit for Modbus, but it's close enough, so we just reuse it rather than to create a whole new model only to have it for Modbus. We have to load it as well. And now I can assign the type system to our device. After I've done that, I can define what kind of slave I want to talk to. Have a look here. It's slave 1, so our unit address is 1 as well. And we just name it slave 1. And then we can define how the fetching of the values, the polling actually should happen. This is the block. This is basically the memory block which gets transferred. For Modbus, it's only a rather small one, and we want to consider that as holding registers. This block 1. we want to fetch two registers, basically these two registers which we defined here, and we want to have a polling interval of 250 milliseconds. Started as a 0, and let's say have a timer at 10 seconds. So if the network blocks or whatever, then the values would be set to invalid if the device doesn't answer after 10 seconds. And we have to define the type, and this is the type definition we put into the memory model. So basically, this is the device configuration itself. What we now need is a driver where this device actually really gets access. And for this we have to create a system node, and let's say to just name it differently, we call that localhost, even if it's the same. And on this, we want to put an Equinox driver. We have two different kinds of drivers. We have the common driver and we have the Equinox driver. The Equinox driver is based on OSGI. The common driver is just basically a Java application. And the Equinox drivers have the advantage that they can be reconfigured at runtime. And we want to access the Modbus device we just defined. And we will have to say that it's actually Modbus. And I just put it on instance number 14, which basically then will result in the actual port number. We name that Modbus as well. And that should be enough to get at least the driver run. To start it from the IDE, you have to create a target platform which contains all the P2 the plugins which you need for running the server part. This is all described in the Eclipse SCADA book, which you can actually find on where is it? There, book.openscada.org, and it's also on GitHub. You can also buy it on for $0 at Google Play and Apple, I think. So going back to the configuration, I'm now going to create the configuration. And as we can see, we have now here localhost, which is basically the name of the system node. And we have the Modbus driver, which results from the name of the Equinox driver. So we have the Modbus driver here, and we can run it. We have looked at the console. There is something happening. Oops, that's the demo. And start from scratch. I put it onto port 2114, and he asked me for the credential, which is admin12. And when I'm looking at the values, I have now here my both two variables which I have defined, and they now have the values 10 and 9 as they are here defined within the test layer. So if I'm going to change the value here to something else, let's say 17, we can see that the value gets updated to the value pretty much instantly. So basically, depending on the pulse cycle you will actually put in. And what you also can see is that the timestamp only changes if the value changes, and so after as soon as the values are in the Modbus driver, all the other stuff happens event-driven. There's no polling involved. Okay, so this is not exactly that exciting, but it would give you the advantage to use all the Eclipse SCADA client libraries to actually get now the values event-driven. But you don't have all the advanced functionality this way. So what we need additionally is a master server, which provides us with some other stuff on top of it. So we have to configure the master server, which should access the Modbus driver. And it's called master, and that's basically it. If I generate the configuration now, we should also have a node which is called master. These things are basically the configuration artifacts. And now I want to rename it to something sensible. So let's say I name it my level, and I want to pull in the external value, and I want to give it some name, my value, for instance. So we have to define where the value actually lives, because there could be several master servers, and of course we have to define where the value actually comes from. And the source name, the name is the value which it will get at the end, and so it's basically a concatenation of the level or the levels, and the name which we define here, and the source name is the name which we can see here. So if Modbus data S1 V1 Modbus data S1 V1, and we explicitly define it as an int value. We also have the chance to put in here some customization tags. Customization tags are a way to put in some additional configuration, and I'll just show you in a minute how they work. Because we have a holding register, it's both input and output. And when I'm generating the configuration again, this is server, and we didn't start the master server so far. I should be able to access the master server as well. Wasn't running admin 1.2, and you can see here my level and my value.v. This is just something which can be customized. So essentially, this value is the same as that one, but we can have some additional functionality on top of it. For instance, we can set a manual value. So let's say, for instance, our device doesn't work anymore. It doesn't answer. This is simulated in this way. So what we can see here is that we can see instantly if the connection is lost. It's marked in a different color. The value is null, and what it can actually do now, I can override this value with a replacement value. Let's say I know what temperature I had at last, and if I have an application which uses the values from the SCADA server, then it can do any calculations or whatever it does using the replacement value, and it doesn't have to use an invalid value in this way. And as I can see, we're pretty much at the end of the time. I actually would like to have to show you how the visualization actually works, but let's have a look at the demo client instead, just to demonstrate some of the additional features which are available. We have a demo server running on one of the servers on the Eclipse infrastructure, and you can download the demo client from the website, which is where is it? In the wiki. Get it started demo system. There you can download the pre-built client, run it, connect to the Eclipse SCADA server, and play a bit around with the values. We have here the Eclipse greenhouse demo, and we have hooked up some of the other stuff. Okay. Yeah, let's basically wrap it up, and yeah.
Great, thank you. That was great. We just have one question. So the question is, you are using custom EMF models for config and types. Why did you not just use the OSGI configuration admin and meta type models?
It's a bit. It was a bit quite some time ago when we started to implement it. The problem with the configuration admin we had was that the actual IDs are not persistent. So one requirement we had was to actually only apply the changes. This is something which I couldn't demonstrate right now, but the generated configuration could be quite large. So and we don't want to apply the whole configuration, because then the whole system gets regenerated, and we only want to change these actual things which really have changed. So we have to do some diff, and if I would use the configuration admin, I couldn't do an actual delta. That's basically one of the reasons why we didn't use the configuration admin.
Okay. Well, thank you for joining us, everyone. If you have questions, you can email them at iot@eclipse.org. And thank you, Jürgen.
And you can always ask us directly.
Exactly. Thank you.
Okay, bye.
Bye.